You've probably seen those incredible videos, right? A massive automated warehouse with what looks like just total chaos. But what if I told you it's actually a perfectly choreographed dance? Well, today we're going to dive deep and unpack the amazing science that turns all that chaos into seamless coordination.
I mean, it's a mesmerizing sight, isn't it? You've got thousands of these little robots just zipping around, crossing paths, and somehow nothing ever collides. It seems impossible. So, what's the secret? Well, that's exactly what we're here to figure out.
So here's our game plan. First, we're going to tackle the coordination conundrum to see why this is so hard. Then, we'll get into the nitty-gritty of what MAPF actually is. After that, we'll open up the toolbox for teamwork to see the strategies they use, check out where these agents in the wild are already working, and finally, we'll peek over the horizon at the next frontier.
Okay, so let's start with the core problem itself. Why is this so darn difficult? You have to remember, it's not just about one robot finding its way from A to B. Oh no, it's about thousands of them, all trying to find their own path in the exact same space at the exact same time without causing a complete and total traffic jam. I love this analogy because it just hits the nail on the head. Each robot, or agent as we call them, is like a dancer. It knows its own moves, it knows where it needs to go, but it has a very limited view. It can't see the entire stage. So it has to make decisions on the fly, all while weaving through hundreds of other dancers who are doing the exact same thing. And the stakes here, they are incredibly high. One little misstep doesn't just affect one robot. It can set off a chain reaction, a domino effect, that leads to collisions, gridlock, and the whole operation just grinding to a halt. In a warehouse, yeah, that's lost time and money. But imagine a swarm of drones in a search and rescue mission. Suddenly, mission failure means something a whole lot more serious.
So how in the world do you choreograph this insanely complex dance? The answer, it turns out, lies in a really cool specialized field of AI. Let's break down exactly what we're talking about.
Okay, here's the official term. Multi-agent pathfinding. We just call it MAPF for short. And you can think of it as the ultimate traffic control system, but for robots. The goal sounds simple enough, right? Find a path for every single agent to get where it's going. But here's the catch, the big one. No two agents can ever be in the same place at the same time. It's not about finding one perfect path. It's about finding a whole system of paths that all work together flawlessly.
And this right here, this is why MAPF is such a beast of a problem. On the left, you see pathfinding for one agent. Easy. Computer science solved that problem decades ago. But on the right, when you start adding more and more agents, the complexity doesn't just add up, it explodes. It grows exponentially. Suddenly, every agent's best path depends on the paths of every single other agent. It's a giant, tangled web of dependencies.
So how do you even begin to solve a problem that's astronomically complex? Well, you don't use just one tool. You need a whole toolbox. And researchers have come up with a whole range of really clever strategies, each one designed to tackle a different kind of coordination challenge. And this just shows you how flexible that toolbox has to be. I mean, real life is messy, right? It's not just about getting from A to B. What happens if a robot just breaks down in the middle of a path? What do you do when new agents are constantly showing up and need a route? Or what if the mission isn't even about a destination, but about having a fleet of robot vacuums cover every square inch of an airport? MAPF has to handle all these real-world curveballs.
One of the coolest strategies is something called the PI method. That stands for planning and improving while executing. The best way to think about it is like using GPS in your car. You don't just map out the entire trip perfectly before you leave the driveway. No, you start driving, and the system is constantly updating, looking for better routes, reacting to traffic jams in real time. It's this continuous loop of planning, executing, and improving that makes the whole system so incredibly dynamic. But wait, if you have thousands of agents, wouldn't the main computer just completely melt down trying to manage every single move? Well, here's the brilliant trick. You have to let go of some control. Instead of making every robot move in perfect, synchronized lockstep, you give them more autonomy. They act on their own and only check in to coordinate when it's absolutely necessary. This dramatically cuts down on the computational heavy lifting, and it's the real secret to scaling these systems up to thousands and thousands of agents.
Okay, so that's all the theory. It sounds great on paper, but where's this stuff actually happening? As it turns out, MAPF is already out there coordinating agents in the wild and in some pretty surprising places. And this is just a taste. We've got the automated vehicles and warehouses, obviously. We've got swarms of UAVs or drones in the sky. We even have autonomous subs exploring the deep ocean. But you got to check out that last row. MAPF is being used to coordinate people, helping manage the different goals of human stakeholders in cultural heritage planning. It's a tool for coordinating any kind of agent, whether it's made of silicon or not.
So, as incredible as all that is, the next frontier is where things get truly wild. Honestly, the challenges that researchers are working on right now, they sound like they've been pulled straight out of a science fiction novel.
You see, up until now, we've mostly been talking about avoidance. Just not bumping into each other. The future is about true cooperation. It's about building agents that can actually understand what other agents are trying to do and why.
Now, this next concept might bend your brain a little bit. It's called epistemic planning, and it's the ability for one agent to reason about what other agents know. So a robot can think, okay, I know that door is open, but does agent B know the door is open? And does agent B know that I know? It's basically giving robots a theory of mind, and it is the key to unlocking some seriously sophisticated teamwork.
And if you thought that was mind-bending, get ready for this. The next step is coordinating with us. Researchers are building systems that can read the collective emotional state of a human crowd. So imagine a delivery bot in a busy train station. Instead of just dodging people, it could sense the stress and the hurry in the crowd and actually change its path to be less intrusive, less annoying. It's pathfinding that's socially aware.
All of which leads us to this one final, really big question. As our world fills up with more and more of these autonomous agents, from self-driving cars on our roads to delivery drones in our skies, our entire society is becoming one massive multi-agent system. The principles we've talked about today are literally writing the new rules of the road for this future, which really makes you wonder, what should those rules be?